Yeah. Okay, so we'll be starting now. Have you guys connected to the Wi-Fi? Okay. So good morning all. So this is the session 3 of our phase 1 of Entirety.ai. So I'll just go through the agenda what we'll be covering today. So we'll be going into the concepts of convolution. So CNN networks are basically the state of the art when it comes to doing any image related tasks. So we'll be understanding how the convolution neural network works and what from the images how they are understanding the features from the images and how it is being used to make any classification model out of it. So there are a few concepts in the convolution which is must to know. So that will be covering in the first part. After that, in the second part, whatever the CNN networks we'll be understanding and how it works, we'll be doing a hands-on. We'll be building that CNN network, and we'll try to deploy it on Flask, so that you get a good understanding of end-to-end implementation, how the model training happens, how you load the weights of the models, how you use it at the time of the inferences. Where your API from the API you might get a request saying you upload an image, and then it has to go, and from the model it has to understand what image it is, and the model has to spit out a particular class, say if this image is of a dog or a cat or something. So we'll do an end-to-end implementation through a Flask web framework. Just to mention, do join Riot. So again, we are stressing on Riot because whenever you join WhatsApp link, you are not able to look into the previous contents what we are sharing. On Riot, it is similar to Slack. You can, whenever you come in, no matter when you come in on the platform, you can go browse back and look into all the materials that we have shared. Okay. So most of you must have attended the previous sessions, and we looked into the feed-forward network, where we were creating a neural network based on a feed-forward network. So now we'll be going into the CNN. So any intuition where you think why CNN is better than normal feed-forward network, or what was there in the feed-forward network that was lacking, which it cannot be used in the when you are talking about the images? Any answers? Sorry. So you're saying there we just had one channel, but we might need multiple channels. But even that, we can again tie it into a single vector and pass it as an input. Okay, so that's what. So the motivation to go over CNNs as compared to feed-forward networks are the following. First, the parameters. If you think about when we are training a MNIST network, we had an input of 28 cross 28. Now there, the image was of 28 cross 28, and then we passed it into a single array of 786, which is 28 cross 28. Now think about if you are trying to use an image of 1000 pixels. The image size is 1024 into 1024. Now the array gonna become big. Now if you keep adding the number of channels, so normal image will have 3 channels, red, green, and blue. Now again you will have 3 channels of 1024. Everybody can hear, right? So That's where. So that was the input layer. So in the input layer itself, you will have 1024 into 1024 of one channel, and then you keep adding, stacking multiple channels in a single array. Now just think this is just one input layer. Now again, you will have a hidden layer. Will again you try to add multiple neurons. So if you just see a calculation happening in an MNIST data, the data size was 28 cross 28 cross 1. So a single fully network will have around 786 bits. But the moment we talked about 200 cross 200 into 3, we have started moving into a 1,20,000 ways. This is just the input. And again, we'll have multiple hidden layers, and the number of parameters in the models keep increasing. Now that becomes pretty challenging because then your network gonna become complex. You will have a lot of parameters to estimate, and then it will go into the overfitting problem. The other thing, important aspect in the CNN networks is the parameter sharing. So right now in the feed-forward network, you had one neuron that was connected to all the neurons in the second layer, right? Whereas in CNNs, you will see one part of the image, which I'm calling as an input, will be connected to few of the neurons. So that's why you can say a single neuron is just looking at a part of a previous layer's images. So that's where the parameter sharing comes into play. And with this, what happens is it gives you the feature which it gives is the translation invariance. Now in the image, if you say we'll be talking about the feature detectors which help us to extract the features from the images. Now consider there is an image of a dog. Now in the image, the dog can be at the top left or could be at the top right. Now the feature extractor that you're going to use has to work wherever the dog is, right? So that was the problem was in feed-forward network that needs to be there. Each neuron has to be connected to all, increases the parameters, and also the translation invariance thing was not being captured there. So we'll look into it how this works. The other thing, the sparsity of connection that we discussed, like the output layer value depends only on a small number of inputs to which it is connected. Okay. Now the one important aspect is intuition. So even in our brain and the optic nerves you talk about, whatever the images that we are processing works through channels. So in the optic nerves, you have multiple channels where we are capturing red, green, blue, and the different features. Now, just to understand what channels are, just think of these channels are nothing but the variations in the images that you are trying to capture. It could be the color, it could be the different gradients of the images that you are capturing. That's what. The other thing is if you talk about the MNIST data set, you have 1, 2, 3, 4. Now, what we were doing, we were converting into a single array. Now, these images are nothing but the shapes, right? So you don't want to lose out on the shape because shape is the most important thing which gives you an understanding of what image this is. Like 0 is known only because it has a circle. If you pass it into a single array, the whole understanding of what shape it is goes out, right? So that's where the whole CNN network you see. So we try to maintain the spatial understanding of what that image is, and it gives a very good intuition. Okay, now we'll have a 3D a 3D feature detector where we will be passing an input image into a n cross n vector. So now here we are not losing out on the spatial information. Right? So this was the feed forward network. Here, if you talk about the CNNs, now we have an input layer which will be passing as a 28 cross 28 into the number of channels. Then we'll have something called a feature detector, and then it will do something and it will give you a final feature a map, which will be further going into a next layer of feature detector. Now, what is convolution? So you will go and see there is a mathematical understanding that you multiply two functions and you try to understand how the shape of a function is changing. That's the mathematical understanding of convolution. But what we are interested in understanding the actual convolution operation in the context of neural networks. Yeah. Yeah. So this we haven't pushed it right now. Just look it here. We'll share. So an intuitive understanding of the convolution is basically a convolution is an operation done to extract features from the images, as these features will be used by the network to learn about a particular image. So in the case of the dog, for example, you can say a feature could be the shape of the nose, the shape of the eye, the thickness of the whiskers. So these are the things that we want to capture from the images that will help us to recognize whether it's a dog or a cat. Right? So mainly a convolution consists of three elements. So three things that we basically look into while doing a convolution. One, the input image. that we have on which we have to do a convolution. The second is the feature detector. Now, feature detector slash kernel slash filter. So there are multiple names we use for feature detector. This is just because actually this the whole convolution and all those things has been there in the computer vision. Right. Also, when you do a say information retrieval, they are also the convolution. So because this field is being used across multiple domains, everybody has come up with multiple names, and that's what we we can refer with multiple names here, right? So feature detector kernel filter is the same thing. So just to understand what it is, it says it's a basically a matrix, n cross n matrix, where we have a bunch of numbers, and these bunch of numbers basically does one task of extracting a particular feature from the image. So if I take an example, okay, okay, okay. So okay, we'll look into that very soon. So we have an input image, which is nothing but the pixels. Now what we are saying, we have a kernel, say 3 cross 3, and now this has to convolve over this input neuron so that we get a new feature map. So just keep a note of what we are calling. This is the input image. We have a feature detector and a feature map. Okay. Now, if you will ask me how these convolutions are basically happening. So if you look into this is nothing but a dot product happening. So what you can say, these 3 cross 3 is being first going over these 3 cross 3, and it's doing a dot product. So 0 into 0, then again all these numbers, 9 numbers will be doing. So I'll just give you an example how this is working. This is what it is. So you have a filter, you have the original image, you overlap that onto a input image, and you do a convolution. Okay. Understand from this. So you have a filter. So you start with convolving from the top left. And here, what basically you are doing, you are multiplying the numbers. 4 cross 1, then 9 cross 0, like this dot product. And you get a final number, which is 2. And that is something you calling, you creating a feature map where you are putting these numbers. Now, again, this number will happen when you convolve this over from here to here. So like this, we'll keep sweeping it over all the image, and with this, we'll get a number. Yeah. Right. Yeah. So the question is, how are we gonna come up with the numbers in these filters? So that's what the neural networks. That's where the neural network plays its role. So till now, in computer vision, people have and the researchers have worked out with the kernels. I've worked out with the kernels where they have over the multiple images understood. If I use these type of numbers, then I'm gonna extract whether an edge, it could be an edge, or it could extract a circular image out of it. So then it becomes a task on us to decide these filters. But with an image, now you don't know what you are extracting and what kind of features it has. So now what we do, we start with a normal feature map, where we feature detector, where the numbers are basically we are saying randomly initialize those numbers, and that is what the neural network has to learn. So the network parameters is now these feature kernels that it has to learn. Any questions here? So this was one paper that came in 2013 that gives a good idea of how the convolution basically works. So what they did, they trained a neural network, and each layer they tried to map it with the image, what kind of feature it is learning from each image. Now, rule of thumb is initial layers basically captures very simple features, which could be a line, a dividing portion, or a change happening between the colors, all those things. And multiple layers keep learning from these previous layers. So it's an abstraction that keeps building on based on these different layers. So if you see the layer one is basically doing a understanding where the edge is, all those things. Now, if you see in the layer two, you just see this image, yeah, and see the feature map what it has understood. So now it has understood, okay, this is a particular circular thing, something. And these are basically the neurons, the numbers, which is basically signifying what feature it is capturing. If you go to layer 3, Now take an example of this map. Now this layer is now able to understand the outline as well as the shape, as well as the hair, all those things, right? If you keep going deep into the network, that's what the actual each feature extractor is doing. It's extracting the features from the images layer by layer. So if you see this dog, now it has nose. Where is the nose? Where are the eyes? Where are the whiskers? Right? Is it making sense? So that's what the paper talked about, how these different layers and what these layers are actually seeing in the images. And that's what we are trying to build. So every layer is kind of extracting different kind of features. And over the time, we are amalgamating all these layers and understanding and building new complex features out of the simple features which are being done at each layer. Now we talked about say we have an n cross n image and we have an n cross n filter and we do a convolution. What if we have multiple channel image, right? Because the images that we'll be working will be having three channels. So then we talked about the convolution over volume. So the operations that we're doing was the same. The only thing changes is now we'll be looking into the depth as well. So the now image is represented by 6 cross 6 into 3. Okay, so now this array is of 6 cross 3 and you have 3 channels of it. Now the feature map that you will be taking, so one feature map will be 3 cross 3, but the depth it will have will be equal to what the input image has. So the convolution has to happen in 3D. Now, what will be the shape of the output? Whether it will be a 2D or a 3D. Yeah, so 2D. Yeah, so initially when we started, we were very much confused about how, because whenever you see a call in 2D, whenever you call it in Keras or Pytorch, it's on 2D. Now, what is 2D? However, the feature detector that we are using is on the 3D. So you have an input image say of 3 channels. Now you are overlapping a filter also of 3 channels. The output will always be a 2 dimensional. Won't be because all these numbers across the channel you have then a convolution across. So you think about a cuboid overlapping a cuboid. And the convolution now will be happening across each filter. So whenever we say we have a con 2D, basically we are saying the output of the convolution will be a 2D. Okay? But convolution is happening at the depth level. Yes. So ma'am, if you see here, we have a 3 cross 3. This is 2D image, and then we have 3 channels here. Now we will be taking a kernel which will have a 3 cross 3 and also 3 as a depth. Now, how many numbers do we have? So if you just think about this number, how this is being calculated. Now, this is being calculated by doing dot product between these numbers and these filters. So that's what here it is saying. You keep adding, you keep multiplying with the filter and the image values, and you keep doing it for all the channels that you have. So you keep doing it for all the channels, and then you get one single number. That's what we are representing. Yes, yes, yes. Right. Right. Now we said these filters are nothing but a way to extract some of the features from the images. Right? Now the images could have multiple features. Now single filter won't do a justice in extracting all the features. So what we do, we stack multiple filters. So then instead of one, we might have multiple filters. Now each single filter has a depth as well. Right? So it's the same operation. So consider from the earlier example, this was one filter, this image. You got some numbers here. Right? Now this you use another filter, you did a convolution, and again you got a activation map, right? And you now this is something which you are stacking. So if we take a general representation, how it is working, generalized. So you have an input image of say NH into NW into NC, where H is the height, W is the width, and C is the channel. Now the filter should have so a filter could be a 3 cross 3 or a 5 cross 5 or a 7 cross 7. Right? You can it's a variable number you can choose based on what kind of task you are solving. So then if you say you stick with FH, FW and FW. Now FH is the height of the filter, W is the width of the filter. Now this NC has to match with what the NC is in the input because you have to convolve across depth as well. Now, how many such filters you're going to use is something that you have to decide, which I'm calling an NC dash. So this is nothing but here, 4 cross 4 cross 2. So if you will see in the research papers everywhere, they will write the output feature map, which is coming something like this. Now here, you see, it's just 3 numbers, but we are talking about 4 numbers here, right? So what has been the case? Like whenever you talk about feature map, when it's an output of a feature detector and an input, they don't mention the channels. They don't mention the depth in which they are. It is assumed that because an input image is of 3 channels, your convolution will also happening on the 3 channels. So here we never mention the number of how many channels we are convoluting over. We just write how many filters we are using. So it's basically 4 cross 4 cross 3 into 2. Does it make sense? Any questions here? So yeah, these 2 outputs are basically because we are using 2 filters. No, so again, this will act as a, so in the next layer, you might think this is your input now, which will have not just 3 channels as we started with, rather multiple channels. So over the layers, multiple layers, what we do, we keep increasing the channels because channels are the only way we are extracting the information from the image. So the depth of the network at each layer, the depth of the channel keeps increasing. Yes. So as I mentioned earlier, we used to predefine the numbers in these filters when we talk about the computer vision problems. There, if we have to understand the edges, then we use a particular filter of particular numbers. But now, because these images can be anything and because there are a lot of features, now we don't have to initialize them. We just initialize with random numbers, and that's what the back propagation will do in the deep learning. It's an art. You have to decide how many filters to do. But mostly, we do a transfer learning in convolutional neural networks. Most of the networks are already fixed, and you get a good idea. But a general idea is initially you will keep increasing the number of channels because from the image you want to extract multiple features, and over the time you will try to do it. We'll go over what all other operations needs to be done in the convolution, and you get a good idea how to create an architecture. Any questions here? So this is important. So this understanding is 4 cross 4 cross 2. Now, if I talk about one convolution layer, what does it comprise of? So you have an input image, you have a filter, you do a convolution, you might have multiple filters, you stack it. Now you have the, and then you apply the activation function. Because till now you are doing just a dot product. There is no non-linearity that you have introduced, and non-linearity is something which deep learning networks are good in understanding, right? Because your data is pretty complex. So these activation functions brings the non-linearity in the network. And once we do activation function, we add the bias, and then we have a particular feature map. So with each kernel, you will have one bias attached to it. So yeah. Yeah, so we had a 6 cross 6 cross 3 channel image. We had a convolution done through a kernel which has a size of 4 cross 4 cross 3. It will give you, say, if a feature map of 3 cross 3 cross 2. Now this two is basically because you are using two filters. You apply the activation, you add a bias, and you get an output. Now this is something which you will be passing in the next layer. So it's the same, like in a feed forward network, we have a weights. So weights are nothing but these numbers, the filter numbers, right, which we have to done. And we are adding a bias just to add more freedom in the network so that it can run easily. This is one more parameter that we keep adding. But if you see in the newer networks, like I guess I'm not running the DenseNet and all those networks, they have kind of say, I want to keep bias at 0. Because already your network is so huge and deep, it has a lot of parameters that it can do a good job in understanding what problem that is solving. So you can also go ahead with saying bias is equal to 0. Yeah, we'll go through that. Before that, we'll just go over a few concepts. Now, the other concepts that come in is strides. Right now, we are saying we convolve the first 3 cross 3, then the second 3 cross 3, right? Now, it might be the case in the image, it's a background, right? So then this pixel is very much similar to this, very much similar to this, very much similar. Now, you don't want to do a stride zero convolution, which is just the next and the next and the next. Rather, you want to shift and do an alternate stride. So it can be you first convolution can happen across 3 cross 3. Now starting from, I don't want to start from here, rather start from here. So the gap that you are trying to give by doing a convolution. So that's what this arrow is saying. I will start the second convolution operation not from here, rather at a shift of 1. This will impact basically how your final feature map, because now you will be doing less number of operations, right? Because you are looking into the alternate numbers. Yes. Is it clear? Other concept comes into play is the padding. So there might be an instance where something important is being represented at the top left. Now, when you are doing a convolution, this number is basically looking into this one, 3 cross 3. Now you keep converging overhead. Here it comes. It might be the case the image size that you are taking right now, it's an even number. It might be something where you are losing out on one. Now, a way to handle such scenarios is basically you add a padding of 0 cross it. So a background, adding one more dimension, not dimension, but one which will help me to look into this. So the concept comes from the receptive field here. So we'll talk about that. That basically see whenever you are doing a convolution, the center of it is basically this number, right? And these are also the numbers that are looking into the convolution. But the next time you are doing a convolution, then again these numbers are being multiplied with the second one. Right? That's what the parameter sharing is happening. Now, if you see, then this is the only number which is not being affected by the convolution which is happening, whereas these numbers get overlapped. So if I have something very important at the corner, and this is something which I want to look into, and my model has to understand this, I want this thing to be specific. That's what I keep adding, so that I'm not losing on the boundary information. Any questions here? Yeah. Hmm. Yes. Yes. So the question is why you are using multiple number of feature extractors when one of the feature extractor can do the work of extracting a particular feature. Right? So each when you say a feature extractor when you talk about the computer vision, there you are redefining the numbers in the feature data. That's what we are not doing over here. We are randomly initializing that number. Now, it could be the case that simple edge detection is not just the feature that I want to. There are multiple things that could be a gradient, the change in the color, the shape. So if you see here, if I have to extract this kind of thing, what kind of filter will you use? So this is an output of a filter, unique one ball. Now if you go over this, if I want to extract it, now this cannot be done through a single filter. It has a number of filters has to be stacked together, which does some different tasks. And then amalgamating all will give you this kind of extraction. Yes, yes, yes. So, so say this is one example where you have this space and you have the pixel numbers. Now, what we are talking about here. So these are the different kind of filters, like predefined. If you select this, it has a predefined number, and if you select here, say this is let's sharpen. Now, this number, if you do the convolution, this filter is good in doing just this kind of task. But there are multiple things that I want to extract. Now, I might need all these filters. Apart from that, few filters, even I don't know how to write the numbers for them. What kind of features I need to extract. So the images, yes. It won't be same. So it depends on how much variety there is in the image. So it might be the case it's a MNIST data, right? At 28%, it's a digit, and you don't have much complexity in understanding what image it is. And no matter how many extractor you use, it will kind of give you the same. Because there is not much information to be extracted. It's just that we are preparing and we are starting saying now I believe there might be 100 features that I want to extract from this. So I initialize with 100 feature maps. And I want my model to learn these 100 features. And over the time, again, new features has to be learned over these features. But details, so it is more related to what kind of image it is. So say it's just a background, then you have a sky, you have a grass. Then easily you know it's a blue, it's a green. Then with few features it can make a difference. Now if I say I need to understand the age of a person through an image. Now I might need to look into the wrinkles. I might need to look other aspects from the facial. Then I going into the very small details because that's where the distinguish will happen, right? Yes. Yes, exactly. So we are kind of extracting 100 different kind of features from the image, which will help us to solve a particular problem. Might be the classification problem, understanding whether it's a cat or a dog, or the different breeds of a dog. So you can think of padding as you are adding more, so you are adding a pad at the end, at the boundaries, just to make sure that when you do a convolution here, the numbers that are being represented here is not losing out on the information on the boundary. It depends. So, what kind of features? That's what. In the image, it might be the case at the corner you don't have much. Also, there are multiple ways. So now, also the padding comes into play when you have image of such size, when you do a convolution and the numbers are not The other thing is pooling. So you have multiple variations in the pooling. It might be a max pooling or an average pooling. So say this was your feature activator, right? So once you do a convolution and you get a feature map, now what I say is do a max pooling and max pooling of size 2. And what it says in 2 cross 2, what is the maximum number? Give me that number. The other variation could be doing an average pooling. So again, the size is 2. So I look into the 2 cross 2 and give the average number. So by this, if you see here, the size of the feature is kind of reducing very fast. Here you had say a 4 cross 4, and if you do a max pooling, you actually got 2 cross 2. Now this is something which we require because say initially we started with an image of 1024 into 1024. Right? Now if you keep adding a convolution, and you'll see the, after each convolution how the size decreases. So one 3 cross 3 convolution on a 5 cross 1 convolution basically reduce the number by 2. So you can say if you start with a 224 cross 224 and do a 3 cross 3 convolution with a 0 padding and with a stride 1, then you get a 222 into 220. Every number is being decreased by 2 at each layer. Now just think of how many layers will you require to bring that 224 to say a 10 classification that you have to do. Saying MNES classification, then at the output you have to predict 10 numbers. So from these many numbers you have to come down to 10. And if you just keep doing convolution, it will take say 100 or 200 layers. Now when you try to do that, then the computation challenges comes into play. Also, your model will overfit. Also, there are a lot of parameters that you have to learn. And also, the thing is, no matter how much information that you are capturing, but is it important to capture everything? Again, the difference between the classification problem of cat versus dog and face detection, detecting the face of the age of a particular person. So in cat versus dogs, I might high level feature say how are the eyes different, how are the nose different, will work for me because it will help me to differentiate between cat versus. Whereas if I want to identify the age of the person, I might need to look into the wrinkles. So the level of details that I have to look into is very important. That's where the intuition comes. When you should be applying max pooling. Now say initially you started with an image and you do a max pooling. Does it make sense? And in which case it will make sense if we talk about these two examples. So with max pooling, if you so you see the idea of a max pooling is to reduce the size of the representation. And they said that we can carry along those features which speaks louder in the image. Right? To lower the number of parameters to be computed, speeding the computation. To make some of the features that detect significant things a bit more robust. Now, if I say I have to do these two tasks, cat versus dog, and identify the age of a person. If I'm trying to build an architecture and say the input image is of say 224 to 224. Now, is it right to include the max pooling in the very beginning, or is it good to apply at the end if we talk about cat versus dog? Yes. At the end. So if you say for the cat versus dog, if I'm doing at the end, so at the end, if I'm considering it's a 20 layer network, then you're saying at 18 or 17th layer. So till 16th layer, you are carrying all those features which might not be important. Because the task that you are doing is very simple. There you might do a max pooling at the initial layer itself. So that I just look into those features which are important. Whereas in identifying the age of a person, there you might need to keep carrying all those features along the network. And at the end, you might need to reduce. Sorry, can you repeat the question? Information, important information will not be lost. So that's something. This is all an art, right? Now you need to have a good understanding of how you are creating the architecture. So what I'm saying, you are correct, but what I'm trying to explain is in cat versus dogs, it might be a good idea to do a max pooling in the very beginning as compared to in the identify the age of a person. Then you might do it at the end. the feature. So from the images, so just think about two images and you see into them, right? And try to differentiate. How much time are you taking? What all features are you looking into to differentiate? If it's very easy for you to differentiate sky versus grass because it's green and red, then initially you do max pooling because the only filter I want to learn is the difference in the gradient, where the edge is happening, right? But in the again, in the age of a person, I need to look into the wrinkles and all those informations need to be extracted. So first, I might need multiple features, the depth will increase, and also I need to carry those information longer in the network. And at the end, I might need to cut it down. So now, earlier we looked into the general representation. Now this is the updated representation, including the padding and slide. So let's work this out. You have an input image of NH cross NW into NC. You apply a filter, which is FH, FW, NC. So again, this number has to be same as what your input image channel is. And this basically tells you how many filters are you using in a particular layer. Now, what you get is a feature map. Now, the formula to tell you what dimension of feature map you are getting is something this. So, what we say, n is the original image size minus the filter image size plus do 2 times of padding. So, if the padding is of 1, then 2 into 1 and divided by the stride. And then you do a plus 1. So, this is the dimension. So, take an example of say 28 cross 28. So, let's do it here. Okay, we'll do an example here just to give an end-to-end understanding how this basically works. So the whole architecture. You have an input image. These are the different convolution layers. Now each convolution layer we discussed consists of the convolution, then adding an activation function, and then adding a bias. The output becomes the feature map. Then that feature map again then becomes the input for the next one. And like this, you might have multiple convolution there in the network based on difficulties based on the complexity of the problem you are solving. And at the end, what you do, you just try to stack it into a single array and make it a feed-forward network, like we discussed before. And from there, you keep reducing and at the final, how many classifications you are doing. Based on that, you can decide the output number of neurons. So let's work this out. So your input images of 32 cross 32 cross 3. You have a filter of size 5 cross 5, and you have 10 such filters. And you want to do a combination with a stride 1 and pad 2. Okay, tell me what will be the output volume size and how this is coming. Try to use this formula. If you have a pen and paper, you can work it out. Just write this information and I'll show you the formula and try it. Everybody wrote this information? So let's work it out. So what is the input image that you have? 32 cross 32 cross 3. Right? The filter that you are applying is 5 cross 5 cross 3 into 10. So now put the value here. This will 32 minus 5 plus you have a padding of 1. Adding of 1, 2. So multiply this. 2 into 2, 4. So it becomes 32 minus 5, 27, plus 4, 31. Stride is 1. So doesn't change the number. 31 plus 1, 32. So the output will be 32 plus 32 into 10. This 10 is basically the number of feature, the number of feature detectors we were using. Right? Now calculate the number of parameters in this layer. The parameters that model has to learn. So what are we learning here? What the model has to learn? Features. Right? Feature extractor. And what is feature extractor? It's a bunch of numbers. So the numbers it has to learn. So let's try to calculate how many numbers do we have in these filters across the channels and with the number of filters. So those will give us the total number of parameters that we are learning. So tell me is the size of the filter that the size of one filter that we are using here. 5 cross 5 into 3. Right? Because that's what the input volume is. So this is one filter. So 5 into 5, 25 into 3, 125 into 5 into 5 into 3, 75. Right? Into how many such filters do we have? 10, 750. Anything we are missing here? Bias. How many bias term needs to be added here? To each filter? 10. So with each filter you have one bias. So 750 plus 10, 760. Depends. You do a 5 cross 5 into 25 into 75 plus 1, 76, including a bias in one filter and 10 times. Yeah. So with this kind of image, with this kind of convolution, we are learning 760 parameters. Now the other concept that came with some of the architectures that was released by Google in 2014. So they introduced the concept of 1 cross 1 convolution. Now you can think of what 1 cross 1 is doing. So now you have an image and the kernel will be having a size of 1 cross 1. Now you are not looking into the multiple numbers from the image. You are just looking at one number. So the operation basically how it happens is something like this. So in a height cross width dimension, you are just looking at one number, but you are looking across the channel. So it's 1 cross 1 into the number of channels your image has, or number of channels your particular feature map has. Right? So this basically is used to reduce the dimensionality. So it might be the case that over the time you are keep adding multiple filters, right? And you are say by third day and you have 100 filters stacked together in the network. Now again, it might be in the next case. Now each filter that you will use, say a 5 cross 5 convolution, so a 5 cross 5 into 100, yeah, to do a convolution, and then you might have 100 more filters to do something. Now again, we are getting a problem of computation. There's a lot of parameters that we need to have to us. So that's where this came into play. Use a 1 cross 1 filter. Done. Then what we are saying, the number of parameters is just the number of the net. So this 5 cross 5 into 100 changes between 1 cross 1 into 100. So just be reducing the number by 25. Earlier it could be 25 into 100. Now it's just 1 into 100. It's a way to reduce the dimensionality of the network. The other place that you can think of the number of activations that we want is the higher the better, yeah? Because that's where it can help to decode the non-linearity in the data. Now with this, you are first reducing the number of parameters. Also, you are adding an activation. It's a plus plus win-win situation for us. So we have introduced one night, say 1 cross 1 into 100, but we got 100 activation functions working for us. It will further help us to decode this problem that we have. Any questions here? So they are basically used for different purposes. There, when we are using a 3 cross 3 filter, we are extracting information and we are looking into a 3 cross 3 part of an image. Now we are looking into a neighboring numbers as well. So this gives a context about that particular number as well as the surroundings. Where here the surrounding is gone. It's just one number that you're looking. But the good part, what happening here, you are looking into the depth. So it's a mismatch that you are doing with the feature. You have 100 features. Now you are doing a convolution over 100 features and you're coming with a one number. Right? So there, what we are doing now, I have a way where I try to combine these different features that we have learned into a single number. So over the period, we have over the network, say by the mid of the network, you have introduced multiple features. Now you have to reduce it down. So at the end, you have to reduce the number. Now, what is the good way to do it? If you keep doing a convolution, again, it will take time. And also, you are not increasing the number of parameters. With 1 cross 1 convolution, you go traverse through the depth, and suddenly it reduces your depth from 100 to a single one. And also, it's doing a mismatch with the features. So 100 different features, it might be a case I want to now combine these 100 features and understand them. So it's a different way that I am making my model to learn things. Yes. So if we look into those Google net networks, inception model and all those, even the RESTnet and NSNet networks, we have a 1 cross 1 convolution. And we basically call it as a bottleneck thing because it basically reduces the computation cost by reducing the parameters. So most of the state-of-the-art architectures have this 1 cross 1 convolution somewhere. So we look further how this plus 3 cross 3 multiple things we can do together. At the same layer, we might do a 3 cross 3 as well as 1 cross 1. So 1 cross 1 is giving me variation across the features. 3 cross 3 is giving me variation across the features plus the surrounding as well. So there are multiple things that we might need to learn in different ways. So these are the different ways we can extract. Eventually, this helps in learning. So the intuition that you can think of, so you have 100 features, 100 different features which are doing different tasks, and you combine them into a single number. So it might be a case now, independently these features doesn't make sense, but if you combine these features, it makes sense. Yes, yes, bringing all the information together into one single number. So at the end, I need to reduce. Now, what is the best way to reduce? One important aspect in whenever you are trying to build an architecture from scratch, you have to keep track of what is the receptive field. So when we talk about the receptive field, say a particular from you get a feature map, right? This is the number which you get after a convolution. Now that number is looking into what part of the image is basically the receptive field. So say I apply two convolution. So I convolve 3 cross 3 over this, I got this number. Then I even got this number by convolving into this part. Right? Now I did a convolution over here 3 cross 3, and again I got this number. Now if you go back and track it, what part of the image this is looking, this number signifies. So this layer it is this part, and this if you combine, this is. This is something very important because at the end, so first thing your architecture at the basic end, if you look into say at the end you are bringing that number into 10 or 100. Now those 100 numbers should have a receptive field, say where you are kind of covering all the image. It might be the case that you are doing a max pooling convolution in such a manner that your receptive field has gone down, and at the end, your feature is not able to look into what actual is happening. And also, it helps us to reduce the error in the network. So it might be the case that you are solving, but your error is not going down in the network. Then what you do a back calculation of understanding what the receptive field. So if I'm looking to, so it might be the case the error where it's happening, that part of the image that I want to understand is not being translated in the end because it get lost by doing the convolution or the max coding. So give a good understanding how you can connect from the end to the back and see what part of the image it was looking into. So that if something important I want to learn from that image, I can tell my model in the error function or something like penalize more if I am looking into something like this. So yeah, so these are the few concepts. The things to remember. Filter will always have the same number of channels as the image. Convolution gives a 2D feature map, although our image and kernels use are of 3 dimensions. Padding preserves the feature size. Yeah, one thing which I must out is also in various cases, it might be the case that after a convolution, you don't want to reduce the feature size. Like if I did the calculation from 32 cross 32, this padding, it again, after that feature, it was again 32 cross 32. So it might be the case I don't want to reduce the size because there are a lot of information that I want to learn. I want to keep continuing with the same size of the puzzle. Right? So it also helps you to keep preserve the dimensions. Pooling operation reduces the filter size by half. You do a max pooling or an average pooling. So if it's a 4 cross 4 kernel and you do a max pooling, you get a 2 cross 2 kernel. Yeah. Let's cover the cost function. So in the earlier sessions we have discussed there is one error function that we defined which gives a good estimate how my model is doing as compared to what actually it has to do. So if the model is predicting something and you have the actual source of truth, you do the difference and then you get to a good understanding of how my model is performing. The difference is basically the error. Now, here we are trying to connect how the model outputs whatever you're getting from the application. How those are clubbed together into error function. What kind of error function we are using? What is the intuition or the rationale behind using those? And what actually the model is doing to reduce that error. Something we'll learn here. So, say we start with a small basic example. So say you have to classify these points. You have blue point and you have a red point. Now, basically, you need to come up with a line which can rightly separate these points. Now, what is the best fit line that you can come up with? So it will be something coming here, right? This is the line which is a favorite. But right now, since you initialize with some random values, you are getting this line. Now, this line has to be revolved and it has to take this straight line. Now, the first question I want to ask, right now you can see there is an error. Now, how you can quantify that error? What are the different ways of quantifying that error? Yeah, what you are saying is basically if I look into the two numbers, then out of three, one is something which is misclassified. So I have an error of one. Right? So now the nature of this error is basically a discrete number. The error could be one, could be two, could be three. How many misclassifications happening? Now the first thing we need to think of whether we need to keep this as a continuous function or a discrete number. Now, the problem with the discrete thing is what? Now you are saying there is an error of one, and you tell the model to correct it. Now, what it will do, it will try to keep moving this line, right? So, what it might do, it might tilt a little, but it still is in this position, but it's tilted a little, right? Now, in that case, the error has not reduced, right? So, a small tilt happening at the same position is not helping you to correct the errors. But every time you are saying I have an error of one and it doesn't changes the line, but again the error is still one. Now the model is confused. It doesn't know what is the best thing to do. Because there is no continuous number key with a single step what the model does, you can quantify and what improvement you have done, I can quantify it. you are stuck in a discrete space. Till the time that line doesn't go and correctly classify my error beyond the base. So at each step, you have to nudge the model, the function, how you are doing. If you take this step, how you are doing, which we discussed in the gradient descent in the first class. So that's what we have mentioned here, discrete measure, counting the number of mistakes it made. However, there is a problem with this one. The algorithm will be taking smaller steps, which are calculated by derivative. So a small step might not be able to reduce the error size, and then it is confused in which direction to move or reduce. However, if we try to go into a continuous space and then measure, say, assigning a penalty. Now, this penalty could be, I have this line, and I say this number, since it is away from this line, I want to assign a penalty of -1. And if it is correct, and since it is correct, but it is close to a line, I want to assign a positive reward of 0.8. This, I can say a reward of 1 because it is far away from this line. So it has more confidence that it is blue. So like this, if you try to come up with a number which can be connected in a continuous space, then at each step, the moment this line changes, it gets a little, you can again see how these points are in reference to that line. Again, you can calculate these rewards and penalties that you are calculating. So, but before that, right now, we have these numbers as 1 and 0. So first step that we need to do is to convert into a continuous space. Right? Need to do a probability. Come with a number which is a continuous. Now this is what I was saying. You have a line, and then I'm assigning this blue has a 40% likelihood that it is blue, and that's what. So anything number greater than 50 is in that favor, right? So because this number is on the opposite side of this space, so this region is all blue, this region is all red, this is misclassified. So the probability of happening blue is 0.4, less than 0.5. It has more probability saying it is red. Whereas you would see it has a higher probability towards. So you can say you are assigning 1 to blue and 0 to red, what it is. But now here from here to here, what I'm saying, I would assign a number based on from where this line is, this number is from the line. Okay. So how can it come from this number to this? That's where you do an activation function. So what it does, it squashes the numbers and gives you between 0 and 1. Any questions? So now think of the same approach. Now, through if you remember the sigmoid function, right? At mid, which says at 0, you have a 50% chance. When it goes to 1, it saturates, right? So if you consider this is your boundary line, now at this point, if a particular point comes, then I don't know what is the right probability. I'll assign a 50-50 chance. That's what your sigmoid function, you see the value at it is at 0, right? And the moment I'm going further away, you see the sigmoid function, S function, it keeps increasing and it saturates at 1. Right? So this is what it is saying. So Wx plus V, which is something which you pass to an activation and you get a number. Number less than 0.5 or less than 0 is something I'm saying as a red. Number greater than 0 is something I'm saying as a blue. Now, to add more weightage on how that number is, where it lies in a particular boundary, which gives me a good estimation of how confident I am in saying whether it's blue or not. So the moment I keep going through this part, I keep adding, the number keeps increasing. So if you take so WS plus E, so calculations you are doing from the network, whatever you are. Take a number which spits out 3 from the neuron, then you are very confident that it's blue. Whereas if the number is split out to 0, then you are 50-50. You don't know what to do. So that's how. So right now, when you do a sigmoid, you get into the probability. Right now, these numbers are basically coming out of from the filing of the neurons before applying the activations. So the output coming from the neuron can be in any space. You don't have a restricted range in which it is giving an output. But the moment you apply a sigmoid, now with the nature of the sigmoid function, it says whatever the output is, I have to squash it between 0 and 1. So now it assigns a low probability to red and a higher probability to blue. Any questions there? So before that, just think about how these models are working, what we are trying to achieve. So we have the data. We look into the actual flows, which is whether it's a blue or a red. Now we are trying to come up with a model that can do a justice in classifying these. Right? So I am learning the model parameters. Now what I'm doing with that model parameters, I want that model to work similarly so that the results coming out of the model is very much similar to the actual social flow. So if I say I have these two models, the one which you prefer is this. Right? So I have to take, this is my bad model, this is my good model. I have to take my model from here to here. That's the task we are doing. From taking here to here, we need to calculate the error. And error should be such that at each step, it gives a good insight of where I should move so that I can rectify my error. Now, a way to calculate how much error I am making is just do some of the you basically take a probability. So what you are saying is, what is the probability of these points classifying correctly? Now you have a probability assigned to this, all these numbers. You say first probabilities of 2 points are red, 0.07. Now this is because 1 point has been misclassified. That's why you see the probability is lower. Whereas if it would have been correctly classified, the probability will be higher. So this is what it is. So you want a model to tune in such a manner where it gives a higher probability. When I say higher probability of classifying it correctly. Because I have the actual source of truth and I want to compare that probability. If my model is working the same way in the way I have classified my data, then this is the right model. Now probability of being blue is 0.12. Now it's pretty bad, right? And the whole arrangement is basically you doing a it's a single event. You must have heard in the probability when to add and when to multiply numbers. A single unit. So in one shot, I'm going to, so this is one task for me. Classify all these points correctly. So I'll keep multiplying these probabilities. So the probability of the whole arrangement is 0.0084. This is really low. This model is not doing justice in classifying these points correctly. Now, if you look at the right model, then these points will have higher probability because they are in the correct space, and if you calculate the probability of whole arrangement. So now we are able to quantify. Till now, we are just looking into them and then saying, okay, this is on the correct side. That's how we are saying it's a good model. But now we can quantify through this method, saying which model is performing better by looking into the probability. So now our task is what to increase the probability to the maximum. That's when I get a good model. The other thing that we have to do is reduce the error. So now, is there a connection between maximizing the probability and reducing the error? That's what the cross entropy will cover. So now you have the insight that you got is maximizing the probability can give us a good model. Minimizing the error function gives us a good model. Now, is there a way can maximize the probability lead to minimizing the error? These are the two terms that we have to link together. Now, right now we are doing a multiplication, right? But if you think about it, these numbers are too small and you are doing across 100 observations. Now you will go into 10 to the power minus 50 minus 1. A lot of decimal places will come in. Okay. But if you talk about the computer handling the float numbers, it's not good when you have a lot of decimal places. Because then the precision goes on a toss. Like 0.0007 and 0.0008, how much is it? And also, if you go and read about how the registers and all those, how these things are stored, you have a greater memory allocated for the points before the decimal, whereas the Mandisa part has very few precision on the registers in which it gets stored. So, what we want to do, we don't want to go into these small numbers, rather, I want to have something which gives me a good a good estimate of how these numbers are moving. Right? So what we can do is basically, so this is what we are writing here. So doing product of hundreds of numbers which range between 0 and 1 could result in 0. Numbers are too tiny and we want to stay away from them. Changing a number when we have product of hundreds of numbers, the product will change that. Another thing was this. So when you have multiplication thing into play, changing changing from 2 to 2.5, the whole number changes very drastically. Right? You don't want such fluctuations to be happening. So what we do, we take a log. The moment we take a log, now what we are doing, we are doing a sum. Log A into B is log A plus B. Right? Now let's try doing this. The probability of the whole arrangement that we calculated was 0.3024. Now we apply the log to each number. Now log in this case 0 to 1 is negative. Right? So you get these negative numbers. Now I say I don't want to play negative, I want to play positive. What you do is you add a negative. Right? So then you make it positive and you get some number here, which is 1.2. Now this value is basically the cross entropy. So if you just reconnect, you are getting a probability. Probability can be very small. And you are doing a multiplication across multiple objects. So that's where the precision will go down. So that's where you introduce log space. You do a log on the probability. So then the whole thing becomes a summation task. And because the log is between 0 and 1 is negative, you add a negative term, make it positive. So this whole task is basically the numbers which you are getting as crossing. So now, if you say you're doing a negative, you added a negative one, right? So there we are saying I need to lower the error, which will help me to give a good model. Since you have introduced a negative term, now you will say lower the cross entropy, better is the model. So here if you see probability going as 1.2. Now this was a bad model. Just because we have changed the space in which that number is represented, we are getting a 1.2. Now our task now is become to reduce this number to 0. Lower the cross entropy, better the model. So now you have, if you look into the multiple packages of Pytorch and Keras, now you have the error function defined as a variation of the cross entropy. Any questions till now? So cross entropy is just a valuation. So a value represented in some format is what we are calling it. So that's like an activation. Activation is a number, but it has come by doing something. That's what it is. So we can say now our goal has changed from maximizing the probability to minimizing the cross entropy, which is essentially our error function. Yes. That's and minimizing the error, now we are saying it's a cross entropy, which we call as the error. So there are few, so we define it might be an error function or a cost function. Right? So cost function is basically the how much I want to penalize. That's where the cost function comes. So both are the same now. So few of the attributes that we want to assign to the cost function should be an average of the losses, be a function of model outputs, and assign higher value to incorrect values and low values to correct. So we are doing a difference, right? So we are looking into how my model prediction is away from the actual. So the difference is something that tells me the measure of error that I'm making. So I want to penalize my model when it's making a bigger error, and less when it's making a smaller error. If you see, I want to do average because I want to right now it might go into the batch, right? 100 images, 200 images. Now I don't want to consider what is the size, image size, what is the batch size. So I just will do an average across all images. So that number is irrespective of how many observations are you seeing. So now you have multiple variations in our cost functions that you can define, and this is basically defined based on what kind of task you are doing. So we'll just look into few, and later we will look into some of the different losses, like 100 loss, and so they are specified for different tasks. So these are basically the two which we'll be using. So for two classes, when you are trying to do whether it's a cat or a dog, you want to use a binary crossing. So let's decode this, what you are doing. So Y is basically the actuals that you have already in the data, whether it's a cat or a dog, 1 or 0. Y hat is basically the prediction that you are getting from the model. Now the prediction of the model is ranging between 0 and 1. Right? So log between 0 and 1 will give you some number, negative number. You multiply with the actuals, which is 1 or 0. So if you are trying to classify a cat, and if that cat is being classified by 1, this number will be 1. And if this is doing a justice in doing a cat classification, then this number will be high, will be 0.8, 0.9. And then this whole number will be higher in doing a negative. 1 minus y is nothing but the other class that you are predicting. So cat is represented by 1. Now 1 minus 1 is 0, and 0 is the representation for the dog. And here again, whatever the prediction you are getting, you do a complement of it, you are getting what is for the dog. And what do? You know it for all the variables that you have in the data. Any questions here? So you can see this particular function is acting as a switch. When it's a cat, then this part will be activated. Whereas if this is a cat, then 1 minus 1 becomes 0, and 0 into 0 is affecting 0. Then so if a cat, then this part is working, calculating the error, and if it's a dog, then this part is working. So that's what this binary into 1 minus 1 is acting as a switch. This part has to be considered when I'm looking at a particular class. Now the other thing could be multi-class categorical cross-entropy. Now this comes into play when we have multiple classes to predict. As we were doing in the endless data set. There we need to understand which digit it is from 0 to 9. Now you have nine classes. So the same thing happens. Now what you are doing, you just all the functions are same. It's just a new term that has been added where you say, now I want to iterate this over all the classes. This is j is equal to 1. So with a particular class, what is the yi? With a particular class, what is the long? So that is one versus all is the way you want to classify, the way you want to train your model. One versus all or one versus one. One versus all, what you are doing is you're saying one class is one, and all the other classes one. But here we are not doing that. Here for every class we are calculating. This j is iterating over all the classes. For each class, you get multiply the probabilities and you get what is the actual. So it's just a extension to this. This year we were just 2 classes, but here it's multiple classes. Sorry? N is the number of images over which you are calculating. J is the classes. So in one forward pass, you are doing one type of error calculation, but over the time you have to aggregate over all the images. But yes, in one so you do a one forward pass, you calculate the error. Now at that, the calculation of error is happening on that particular axis. So what you are doing when you say endless, what you is you be converted into a dummy variable, 140, 40. So every number is represented either by 0 or 1. So when the number is 1, we are saying we have found that number. Right? And if it's not, then it's a 0. So every class is being represented by two numbers, which is 0 and 1. That's what it is. So if it's a correct class, then this part will work. 1. So 1 we are assigning it is the correct class and 0. So just imagine we have 10 classes, but with one class we are representing by two numbers. If it is correct, then 1. If it is not, then we are saying 0. That comes between 0 and 1. So that should log y will give you. For each class, you get a number between 0 and 1. So with binary, the easiness that comes into play is with each class, if you're assigning two numbers 0 and 1, then it complement whether it's not there, then that signifies the other class is there. Because just two classes. If that is not there, the second could be there. But in multi-class, if one is not there, there are 9 other things that can be there. Yes. It creates over all the classes, and for each class it is represented by two numbers, 0 and 1. Right. So, say you are representing, say, cat versus dog. Say you have three different breeds of dogs. You have 5 classes there. Now, each class will be represented by 0 or 1, binary number. If it's so, if you see an image and if it's a correct breed, for that particular correct breed class, you can say 1 and all others will be 0. Right? In the second image, if the second breed, then that number will be 1 and other 0. So for a particular in an image, you will be one breed of dog. So that particular if it is success, for that particular class, you will have one, other will be 0. Right? So that's what it is. Yeah? And between 0 and 1 is something what your model is predicting. And I want to stretch it to 1 if it's a correct class. So that's all for the first session. And we'll break for 10 minutes, and after that, we'll do a hands-on of trying to build this convolution neural network and try to deploy it in large scale. So if you guys have a laptop, you can will help you to install Pytorch on the local system and one or two more web frameworks like last. Yeah, and we'll do a hands-on. So we'll stop for 10 minutes. Okay. Thank you.
So everyone can open collab. So I'll just explain what's the flow around here. So we'll train some, the heaviest, neural network on collab, and then download the waves, and then deploy it in your local. Okay, so the inferencing part will be happening on your local, and training will happen in the server, which is collab. Right, this is the general practice which is followed. Like if you have AWS instance or something like that, you train out there and then deploy it into a server. And so it will give you an hands-on, end-to-end feeling of how the training is happened, what's the training process, how you load the weights and plug it into a API, and then add a front-end layer to it, and then how the callbacks happen and how the push happen, right? So and how the result gets displayed on your screen. Right. So this end-to-end implementation will be done. So you guys can open Collab for the training part. We'll do the training from scratch, right? Yeah. So yeah. So type in. So type in collab dot research. Create a new notebook. Uh, let them take GPU. So after training, they don't need a GPU. CPU. So create a new collab file. Let's call it mnest deployment. Just give this new notebook, and you get your new collab here. Yeah, and then just import all the dependencies. So, uh, so, so import your torch, right? And then import, what else do you need? Torch NN, and then import your functional library as well. So you just name it as this, and then import any optimizer which you need. So that's it. Yeah. Can everyone hear me? So you take in your optimizer here, and then just name it as optim, and then so import anything else required. You can take in the all the transforms and all required transform and a data loader, so you can do it this way. So here is your MS data stored. So we have to take this, right? So then, here is your transforms, right? And then yeah, that's it. So we are done with our all our imports, right? Just run that. Okay. So now you can create a class which will define your structure of your model. So let's create a class now. Uh, right, and then after passing in, so we do a definition of init, and then the what do you call the feed forward, like how you do the feed forward definition, right? So here you do all your init declaration. So you're actually extending the what do you say the new NN defined by torch, right? So that's the reason why you're calling this super stuff and all. So you are inheriting the function from there and then overriding it here, right? So here you're calling in the neural net, right? So right now my function class name is NN, so I'll just pass in this, right? And then I pass the object as well, and I give an init, right? And now I start defining the structure. So what I'm planning is first we'll take a CNN layer, right, which will be yeah. So so what I'm planning here is if this is your entire image, we'll do a 3x3 convolution on top of this, and then we'll do, let's say, a max pool layer. I mean, we pass it through a ReLU, right? You know what? Everyone knows what a ReLU is, right? and these 3 cross 3 is a con 2D one. So normal 2D convolution on this, right? And after this, we'll do another convolutional layer, right? Let this also be 3 cross 3, and let's pass this through a max pool. So everyone knows what's a max pooling thing is, right? So max pooling is like, suppose if it is 2 cross 2, so if this is your entire image, and let's say I'm taking this region, and if my filter size is 2 cross 2, I take the max of this, right? So if the max is on the upper right, I just take that particular, what do you say, element, that particular element, right? Uh, so I'm defining the first convolutional layer, right? Uh, everyone has got till here, right? You understood end to end what's happening, why I'm calling all these libraries and what I'm trying to do here. So, so from this, library, I'm getting the convolutional layer, right? So you can do it this way. So con 1D can be given like this, and then 2D can be given like this, right? So whichever one you require, right? And this will be the first parameter is the input channels. So when you take MNIST, that is 28 cross 28 cross 1. So the channel size is 1 here, right? So it's a like a uh, so it's a 1D 2D kind of structure is being in place. It's not a 3D kind of image. It's not RGB. It's just grayscaled 2D image. So the input channel is 1, right? And the output channels can be anything. So let's say 20 for now. So what it does here is it tries to create 20 such outputs of the image after doing a convolution operation. It'll take in 20 kernels, okay, and then try to give out 20 outputs. So I'll just show it to you how could it look like. One second. Yeah. So if this is your image, right, which is 28 cross 28, right? I'm trying to do a convolutional operation, which is 3 cross 3. So this is my single channel, right? Which I'm going to run this over this sequentially, right? So this will give me one output, which is 26 cross 26, right? Everyone understand how this transformation has happened, right? Right. Now, if I take 20 such kernels, right? There are such, like, let's say there are 20 such kernels, so I'll get 20. So I'll get so many outputs as well, right? So the entire size of this would be like 20 cross 26 cross 26, right? So 20 is the new number of channels which has been created. So right, so this is my input channel, right, and this will be the output channels. Output channels is this, this part. I mean, this is my output channels, number of them, right? And this is my kernel size, which is nothing but this. This is my kernel size, which is 3 here, 3 cross, since it's a 3 cross 3. And generally we are using a square kernel. So since it's a 2D one, right? So that's the reason. And then this one stands for stride. So everyone knows what's a stride, right? So it's like how much gap you need after every convolution operation. So when you finish, let's say this convolution, so how much you want to move to the next for the next convolution? So is it by one pixel or is it by 2 pixel? So how much shift you want after every convolutional operation? So by default it should be one, right? It can be two, three, or anything, right? So after this, you can do, you can also create the second layer as well. How do you want the second layer to look like? So it depends. So how many channels you want to feed in here, right? So we could maybe feed in, let's say 20, right? So 20 from the previous one, right? And now how much you want to expand or contract? How many channels you want it out as an output? So let's expand it further, right? And then let's give a similar this thing. You can even give a 5x5 here. It's all upon you. So mostly, to try to figure out the right kernel size, from trial and error. Right? But in general, if you want a good hardware support, you always go for a 3x3 than a 5x5, right? Uh, 3x3. But you can even go for 5x5. It's all up to how you want to go and try out. And this is tried as one. It will be the same, right? Now you can also do some kind of a fully connected at the end. So you can name it as FC2 or something, or F1. So right, what does this linear thing do? So it's nothing but a fully connected, like the output of this, will be fed into a number of neurons. So here, let's say if I give it as, let's say 500, so the output of this, right, will go to 500 different nodes and, give a fully connected output, right? So So this could be, first you have to define what kind of input you are trying to give, right? So it could be 5 cross 5 cross. So right. So I'll give you what kind of model we are trying to do here, and then maybe we'll talk more about the structure. Yeah. So the general structure what we are following here is we take the input, right, 28 cross 28, right? We pass it through, let's say, 3 cross 3, right? And since here we are getting in 1, we are converting it to 20 such, features, right? And after doing that, we are passing it through a ReLU, right? To, pass out only the activated features and not the, deactivated ones. And then after doing this, we'll again do a 3 cross 3, right? Or maybe we can do a max pool after this. So after ReLU, we can do a max pooling to to reduce the size. So what's the size over here? Can anyone guess? After a 3 cross 3, what will be the output of this? 26 cross 26, right? And so in PyTorch, how it works is, so you have to give the channels first. So it will be 20 cross 26 cross 26. So this will be the output tensor, right? And next will be a ReLU. So there won't be any change in the dimensions as such. It will just pass in the activated features, and rest will be zeros, right? So ReLU looks like this for someone. Sorry. So it looks somewhat like this, right? So rest all will be zeros and everything will be as it is, right? And then I'm doing a max pooling here. So max pooling, what it does is so it will be a 2x2 max pooling. So it just reduces this to 20 cross 13 cross 13, right? Anyone has any doubt in this operation if it is a 2x2 max pool? Right, so what it does is it takes in this, moves it on the image on this, which is 26 cross 26, and it just takes the max of this. So if this element is a max, so it will go as an output as one of the one of the values in this 13 cross 13, right? um, so after doing this operation, we may try out again a convolution operation, which is 3 cross 3 comma, how much did we give? 50, right? So input channels are still 20, and then the output will be 50, right? So this will spit out 50 such channels, right? And after doing this, I'm passing it through a uh, linear layer, or we could even do a max pooling here as well to reduce the number of linear activation. So we can do a max pool again, right? So after doing a max pool, what's the output? Can anyone give me the output of this? Anyone? So after a 13 cross 13, I'm doing a 3 cross 3 with a channel size of 50. So what's the output of this? After this operation, what's the output? Yeah, 11 cross 50, right? So after doing this, and here is my 50, right? So after doing this, I'm passing it through a max pool. So after max pool, what it does is it converts into 50 cross 5 cross 5. So it takes the floor value. So max pool, what it does is it reduces the height and width by 2, right? So if the max pool's filter size is 2 cross 2, right? So after doing that, it takes the flow value. So it will be 5.5, right? So it takes the floor, which is 50 cross 5 cross 5, right? So remember we defined two so this will convert. So we are slowly trying to reduce the numbers from 5 cross 5 cross 50 to 500, and then from 500 to, let's say, 10. So the output, the end result should be 10, right? So that's the reason why I'm giving 10. So FC1 is my first fully connected layer, and FC2 is the these are just names. You can give in anything. Okay, okay, I'll just explain it. So after doing this, right? Sorry, after doing this, huh? Yeah. So you have 50 cross 5 cross 5 after doing this entire operation, right? So now you cannot directly do a prediction on this, right? So your end result is quite sparse. So you have to reduce it, and you cannot reduce it easily. You have to do it slowly, right? So what I'm doing is I'm taking the filter size, I mean number of filters, and then which is five, and the output is 5 cross 5, and I'm converting this into 500. So how am I doing it is by passing through a fully connected layer, right? So this is that fully connected layer. So it just takes the input as it is, and mixes it and merges it and gives an output of 500, right? And after this, I'm doing the same thing for this 500 and converting it to 10. So we need 10 outputs, right? So that's the reason this is after 500, it's 10 now. Everyone got it, right? So yeah. So in forward, I'll define the entire structure. So here I've just given the layers, right? Here I've just defined what are the layers we are using, and now you'll get in the feel of that. So first layer will be this, right? So yeah, and after doing this, you just pass in your input image, right? So after passing your input image, what you're doing is you're passing it through a relu operation. So you can do it directly here. So you can give relu and then uh, the output of a convolution. So first you get your convolution operation done, and then you do a relu on top of it, right? So it's kind of an activated convolution operation. Got it? So after doing this, where is this f coming from? It's from this functional library. So it has all those activation functions defined in the right. And what you can do here is you can again take in this and then pass it through a max pooling operation, right? You can do a max pool or an average pool. So you can again take in f and then do a max pool on top of this. So you have to just give in the parameters, which is x, and then what kind of kernel size you want, which can be 2x2 or 3x3, but generally we use 2x2, right? And oh yeah, you have to define like what kind of one you want. There are many such max pooling layers you can do with try to do with 2D itself, and then after this you again so now after doing this is our first operation of convolution and activation and then a max pool. You can repeat this with the second convolution operation, right? So you can again take in this, right? You can take in this and pass in your input, which is x. Again we are just passing this back here, and then here you can again do a relu activation. So again, you can pass it through a max pool operation again. So you can just repeat the same thing, right? So are everyone done with this? Okay, so let's comment out what's the filter size here, right? So here the output will be 26, right? It will be 20 cross 20 cross 26, and then so here uh, it will be let's say 13, and then over here it'll be let's say so it's over here 50, right? 50 is your output features, and then here it will be 11, right? And so here it just divides by 2, so it will be almost like 5. You take the flow value, right? And doing this, so we can. So since we have all this defined, now we are trying to use your fully connected, right? So in fully connected, you can do it like this. So define it self dot c1 in your input variable x, and then so the output of this will be 500, since you have given the output here as 500, and then here the output would be 10, since we have to do the activations and stuff. So after this, you can return the sort of you can do a softmax or a log softmax. It's up to your choice, right? So everyone knows what the softmax is, right? So you can oh yeah. So before this, um, okay, yeah. So I forgot to tell you one thing. So since right now the structure is in a 2D structure, right? So it is 50 cross 5 cross 5, right? And this is a linear layer, right? So you have to flatten this up. Okay, you have to flatten this input. So how you are going to do is there's a function called view in Pytorch. So what it does is it takes the entire thing and analyzes it in a straight line. Okay, it makes it into an array, right? So so here you have to pass in your so -1 does that, and you have to pass in your input size. So the input size will be 50 cross 5 cross 5, and you have to pass in your input variable, which is x. Okay, so it actually takes in this, right? So you understood this, right? So it just flattens it up, right? And okay, so everyone got the stuff, right? So this will create the structure, and here you are doing a feed forward, so it gives entire operations as well as the structure and how you should use those structures and how you should pass in the functions and then create a entire neural network, right? So this so now I'm creating a train function and the test function and how you have to load the data set and how you have to pass it through this network, right? So you can pass in your model and then few arguments which will define you later, and then you will pass in the device. So It's a good practice to pass in all this information, to know which are you doing it on CPU or a GPU, right? And it can give you a train loader and the test loader. I mean, optimizer, which optimizer you want to pass in, and also to give out the number of, not the number of epochs, which current epoch you are going to execute right now. So while the training, right? So this model is clear, right, to everyone? Right. Okay. Um, so let's do this. So I might explain you this later, so just go on with me right now. So my train loader comes in a package. So it has all this, functions. So if you do an enumerate, it just splits it up, and you can use it like this, right? So it will give you a batch ID, the data. The data is the image here, pretty much, and then target is your, prediction, right? So you do that, and then just make sure that all these things are happening in your device. So you can just do this. So you are giving this to device function. So whichever device you wanted it to run in, it will run in that. And the same thing goes for the target as well. Then here you are defining which so you are taking your optimizer and making sure that all your old previous gradients are zeroed out. So you just do a zero grad here, right? And after doing this, you just take in your output of the model. So you take it like this. You pass in your data, and then you get your output. So after doing this, you do your loss, right? So you can define your loss over here. So you can use, there are different types of loss. So right now I'm just taking this loss here, right? And this your output, and then you give your target, right? So it just takes the difference of between these two and computer loss here, um, right? And then you can pass in your loss backwards. So to pass in that, you can give in loss dot backwards. So, right, and then you give your optimizer a step, right? So after every batch, you're passing in your losses and then passing it to the optimizer. So the optimizer takes the loss in and then tunes in the weights as it is, right? So how to do that is like using this function over here. Right. So this will okay. So this will do that one gradient descent, you can say, one iteration of the gradient descent, right? Later on, I'll tell you how we are defining the learning rates and as such. Right? So you can, maybe print out your this thing. So you can print out all your epoch, which epoch it is coming in, and how what's their accuracy and all those stuff over here. So based on your batch IDs, you can do this. Right? So maybe after every let's say 10 batches, right? I'm trying to do this. And to print all this stuff like so I'm giving the train. So this will format your output, right? And then so maybe I'll just give them the so it will show which epoch you are currently in, right? Then you can okay. So you have to give a dot. Right. So this is the way you generally do it. So you can even add in your loss here. So you can give it as loss, and then you can pass in your the loss you're trying to give in. So this loss is in a tensor form. So get the value, you use this item, right? So you use your item here, and then you can maybe run this. After doing this, so this is our train method here, right? So anyone has any doubt here on the train method? Which one? Okay, so it makes sure that if you are in a food, so if there are two kinds of devices here, one is your GPU and one is your CPU. So if you want to train your neural network in your CPU environment, the device is set to CPU, and if you want to do it in a CUDA environment, that is your GPU. So it's like wherever you want to move it to, you can move it over there and make sure that it's the same thing in the entire flow, right? So general happens, what happens that while you're doing your stuff, you kind of mismatch it. Like your target is somewhere, your data is somewhere, right? So you're making sure that everything is into a single place. So it's just a check. You can ignore it as well, right? Yeah. So it sets all your gradients, previous gradients, to 0. Yeah. So similarly, I'm trying to do the test function here. So there are a few changes you have to make. So you are passing in the arguments, device, and then instead of train loader, you're passing in the test loader here. And then you don't need an optimizer here because you're not doing a gradient descent operation. You're just doing a test evaluation kind of thing. So you just do a model.eval here, where you're trying to see how is the model performing after the train operation. So you can skip this maybe. So we are checking how much is the loss here. So initially it will be 0, and then trying to see how much is the. We'll do it later. So you're making sure that everything has no gradient involved from the previous this thing, the same thing. And, then you are trying to iterate through the train set, I mean test set. So you're doing the same way, data. You're passing in your test loader here, right? And then after doing this, you're trying to see what's the you're trying to see the prediction here, so you can use the same thing here. What? You don't need it. Yeah, yeah. You can remove this as well. Enumerate, what it does, it just gives in the form. If you want in the batch IDs are here, so you can give it that over here. But we don't need any IDs here, so we can remove that. And you're taking here the loss and again doing the same stuff as before, but you're not going to do this loss backward, and you're not going to do the optimization step. So you can skip this, right? But then we should we should start appending this and doing it for the entire data set. So you can do it like this and then start appending it and summing it to the same thing. So here you're trying to calculate the loss for the entire data set of the entire train set, right? So you can do it this way, and then and make sure you just do this item. So here everything is in a dot tensor. So to get the value, you have to do this, right? And then what you can also do is that you just given two device here. So everything is initialized to the same device, and then you're passing in all your stuff. So here you can give your reduction if you want, how you want to reduce it, but the hyperparameter you can change it out. And, so here you're trying to check what's your prediction. So you do it this way. Yeah. So so this will give out your actual prediction based on the softmax result, right? But you cannot do a loss calculation based on that. You do it for entire all the classes and then take in only the first class and the maximum class and then pass it your prediction, right? And what else you can do is you can check in what's the correct value as well. So it just gives the maximum, element in that particular tensor or array. So now we are trying to equate this with the target. So you can do it this way. So what it does is so this is trying to measure your accuracy, right? So the way to do it is you're trying to trying to equate your prediction with respect to your target, right? And after doing that, you can after that you can do a sum operation and then divide it by the length of the target, right? So you can do it this way. Everyone got this, right? So you're trying to sum it out and then you're trying to pass in the item of it. And then so, so what we are trying to do is we are trying to find the average test loss here, right? So based on what and all you have accumulated here, and the same thing will happen to the correct as well, to the accuracy. So you can do the same thing here. So now you can print all this up. So the way you can do it is, and so you can either store it as a variable or something like that. So name it as your test loss, then format it, and also you can give your accuracy, then format this as well. You can run this up. So after doing this, you get you can see the accuracy of your test set and then the train set, right? You can see how is your model performing, and based on that, you can take in the decision if your learning rate is increasing, decreasing, and tune in your hyperparameters as well, right? So after doing this, you can create you can create your main method. So it will. So here I'm trying to create all the arguments. So I'll just call it as dict. Uh, so here are just the basic hyperparameters which can be used. So one can be a batch size, So your batch size can be 128. You can even do a 200 or 300, whatever you want, based on your GPU, CPU memory. And then after doing this, you can give your test batch size as well. So you can keep it anything. So I'm keeping it 1000 since you don't need any much memory for your test set. So you can just directly load it and you get your end result as your feed forward network. You're not doing a backprop, so you can keep it huge. It doesn't matter. And then you can give how many epochs you want. So you can set it to 2 or 5 maybe. And then you give in your learning rate, how much ever learning rate you want. Right, and you can give in your momentum if you need that. So this will be used during your optimizer, right? How much momentum you want to. So momentum is like when you're doing a gradient descent, right? You want to see how fast you want to move up. So you can say it's like a gravity. You can treat it as a gravity quotient. So if your momentum is high, so you're trying to you have a less computation, let's say. So if you have a good computation power or let's say money or something like that, so you can uh, keep it low or something like that. Yeah. So right now I'm just setting my momentum to be, let's say, zero point 0.7 or something. You can set it anything. So maybe I'll set it to zero point 0.5, right? So after doing this, you can. So this is actually a dictionary which is loaded. So there's one method to create this as an object and then later on use it. So I'm trying to do that. So yeah, yeah, you get this yesterday. Yeah, yeah, yeah. 2014, 13. Yes, yes. Yeah, yeah, it was. No, he didn't. So if you are trying to do it production ready, so you try keep this in your INI file. So in INI files, you keep your configs and all your hyper parameters you want to tune in or something like that. You can even keep in your file names of wherever you want to save your weights or whatever you wanted. So you can import this and then put it into this to get in stuff. So this is how you do it in production. So I'm trying to follow the same thing so that you guys can get that same intuition. So so what it does is it takes your dictionary and tries to tries to run through it and create an object from it. So it goes through your entire what do you say entire values and tries to get all the, what do you say, key value pairs, and then creates an object on top of it. So I'll just show you how it does that. So you can pass in multiple dictionaries here. So currently I'm just passing one. So after doing this, you can just so here is the key and here is the value. So you can get the value like this. So after doing this, you can go back and set the same thing again. So if there are any keys left in cogs as well, so these are console keys. So you can use these as well and put them in your object. So you don't have to worry about how the object is formed, right? So it's all dynamic. You don't have to do mapping or something on that sort. Same thing. You can yes. So after doing this, you're done with your class, and then you can use that anywhere you want, right? So, so now let's define our main method. How it should run. You can either use um, CPU or GPU. You can define that here, and whatever is available based on that. Right? So you can to check on if you have a CPU or GPU available. You can use this function. Good is available or something like that. Yeah. Or, so it will. Oh yeah. Sorry about that. Yeah. So currently I just set it to CPU mode. So if you do it, switch over to a GPU mode, you'll get that thing. So it's okay. It's fine. You can even train this neural network on a CPU, right? So so right now I'll just set this use to false. Um, then so so I'm trying to set a manual seed so that everyone gets the same result, right? And so that so since we are going to initialize all the weights randomly at the starting, right? Everyone gets the same weights, right? And yeah, and you can set your device as well. So which device you want to set in and pass it to the above variable. So so there's one function. Uh, this is available. So there's based on whatever you have, you can use whatever device you want, and then you can set in what and all variables you need here. Remember that quarks which I had set, and you can pass in over here. So here you can define in how many workers you want, and you can also use how much memory you want, or if you increase that, how much size you can pass into your network, right? So any other environment variables you want, you can just set it in here. So I just given a number of workers. So you don't have to give anything if it is that use CUDA, else you can maybe pass it as empty. So so this is majorly useful if you are using GPUs or something like that. You want to do some distributed processing, right? So you can give in the workers here, and then if you're not using it, you can just pass in the false thing. So currently we're not using anything like that. Yeah. So, you can maybe keep it here itself. And what else you can do is you can call up your train loader and test loader and load in your data set, right? So, so we are using the torch utils library to get in the data. So you have to just give in your data set here. The name of the data set is MNIST, as you all know. And pass in which folder you want to keep it in. So maybe we can keep it over here. And so yeah. Oh, sorry. Um, okay. Yeah. So here you need to mention which set you want. You want the train set or the test set. So you have to give the train set to be true. Right. And then you also given, so it has to download it. So give that also. Then so if you want to apply any transforms to it, you can give that as well. So actually, I found you don't have to normalize here anything, because so if you have a data set where you want to normalize something, so you can even give a normalize function here. So it is transform dot normalize between what values you want. So you can give the scales as well here. So right now we don't need it because the MNIST data set is already normalized. So it is between 0 and 1 by Torch default. But if you do it through Keras, it will be between 0 to 255, right? So you don't have to do that. So you can just copy paste the same thing and do it for the test set. It will be called as a test loader or something, and then you can give a train as false, right? Pretty much the same thing. Oh, sorry. Oh, so typos keep on happening. So, oh, I think so. Well, so here just downloaded the entire data set and what's up? First, क्या हुआ? सही तो था. Data set. उधर जा, बंद कर. एक और बैच है, सभी बात करो. So, yeah, I just forgot to mention the batch size, right? So you can get the batch size from the quarks variable or the args variable. I might have defined it over here, right? So, for that, yeah. So you can use this and then. So you have to just pass in this dictionary which we created here, right? And after passing it through this object, you can just pass in your batch size. So, so it got my batch size, and then you can do the same thing for the test set as well. But then here it will be the test batch size. So you can give that here. Right. Okay, so I might have missed a parenthesis. So, yeah, okay, so it's a good practice to keep the data set outside. I'll just do that. Okay, which transform. So now you can pass back that same thing over here. Right? Um, yeah, with this. So do the same thing for your test set as well. Right? And then just mention here as your test set. Okay, so it's mostly this. Okay, yeah. Sorry for that. Yeah. So pretty much we're done with the loading part now. So we have to just pass in through the loop. So are everyone on board here? So did everyone got through the test set and the data loading set? I'll give you just few minutes to settle. Yeah. Now it's fine. Right? Everyone can view it, right? So after this, we have to just set in the optimizer and then pass it through the trains, test and train the model, and then we are done with the optimization part. So now I'm just initializing my model, so it'll be same as my class. So my class name was I think NN or something, right? Yeah. So just give the same name and just make sure that it goes to the device which you wanted it to go. And okay, so I think the class wasn't defined or something. We did run this cell, so let's run this. Yeah. So after doing on the class, we can given the optimizer, which optimizer we want to choose. We can go with SGD or Atom or whichever you like to. So let's do that. So I'm just calling this library and getting the SGD optimizer. So here go. So here I'm passing in my learning rate as well. So model parameters are nothing but the weights and LR. So here we have stored the arguments in this args variable here, right? So just LR. So you have to just give it as args.lr, right? Then anyone given the momentum if you need. So after defining the optimizer, you can, pretty much are done with. You have to just initialize the batch sizes and, iterate through the epochs. So, so let's do that. Let's keep it in the range or something. So let's define it as epochs so that the epochs are two, so it will be so one and two, right? So that's the reason I've done this. So uh, let's call in the train and the test here. So in the train, we have some parameters, so we have to just give in the args. This is nothing but an object which has all the hyperparameters, right? And then given the model as well. And after passing in through the model, we have to give in the device name and the train loader and the test loader. I mean, here's the train loader, and down there you give the test loader and go to optimize. So copy, it's pretty much the same thing. So, so we don't need an epoch and an optimizer in the test loader, just given the test loader here. Right, so let's see how it prints out the epochs. So it seems it's not yet defined, so maybe we can give in directly as args or epochs. So there seems to be some issue with the optimizer. Anyone else? You guys can go through this. I'll just figure out what's the issue here. got it. I forgot to print out the loss. So you can see the losses are decreasing, and then after the first epoch itself, uh, so everyone are done till here. Maybe I'll give some time. So you can see it's 100 minus this, so it can be around 95. You can say. Let it train. So you understood, right? So in a for loop, it's going through every box. So if your number of epochs is 5, so it iterates through it and passes it to the test and the train and the test set, and it does it for every epoch, and shows the loss and the accuracy as such. So there's an issue with the test set, I guess. So oh, okay. So I forgot to initialize it to 0, maybe. So let me do that. There's my test set. Yeah. So I'll just do that. Let's train the neural net again. So if you have any issues, you can. Okay. So you guys have reached till here, no? Uh, Aman and Utkarsh will help you guys out. Okay, so test has issue still now. Yes. So I have to give it as output here. So let me do that. So uh, I'm still debugging the code. Okay, so there was one out mistake here. You have to make sure it is output here as well. It's taking the output from this and doing an argmax operation on that. So, much here. What? Where is that? Uh huh. Okay. Okay. Let's remove that. It's a default thing. Maybe it'll take care the argmax argument. Let me remove this and uh, it's nothing but dimension. So it's keeping the same dimension as it is. It's not altering anything on that. So by default as well, it keeps the same thing. Yeah, I just removed it. Just remove any keep dims if you guys have keep dims in the test function. Go to your test function and just remove that. While using an argmax, or maybe I'll just show it to you. Yeah, 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 I've just done that. It's correct. So, so this is nothing but the accuracy. Yeah, bye. Yeah, so here it's showing the text test loss as well. So it has reached to 96 accuracy, 96.2 accuracy. You can move on. Yeah, argmax. Yeah, yeah. So this is my argmax. Okay. While it is, say, how many people have reached the training stage can raise their hands. So anyone has compiled this? Reach till here? Okay. Is anyone having an error? Okay. So right now the model is, performing pretty good. It's almost reached 97 accuracy. It's at the fourth epoch. So meanwhile, I'll define how to save the weights, right? So you can do it as model dot save diff. So I'm converting the model into a dictionary and then storing it in my local. So here you have to just give in the model name. So I'll just give in can give it as it stores in PT format. You can give it anything up to you. So after doing that, it just saves in. So it'll run this. Okay. Where? Okay. Yeah. This. Anyone else getting some errors? I can help. So, so here you can see my model has been trained, and I'm trying to save it here. So there's a typo here. Just make it as model. Yeah. So this is the way you save your weights. You call in the torch.save method, and in that you pass in the dictionary which you make. So and here you give in your file names. Right. Yeah. So let's download it. So the way you download things from your collab is using this. You import the google.collab files library, and then you just call in download, and just given the method name here. So just given the method name here, and then just click on download. It will just start on the downloading part. So yeah, you can see the weights have been downloaded here, right? And maybe even visualize it. You guys have something. No, sorry. Yeah. Okay. Oh, it's just call in from collab import files, and type in files.download with the file name. It'll just download it straight away. Who else is facing any issue over there? Just it. So how many of you got the weights downloaded? Can you raise your hands? You got your weights downloaded? Then you got your weights downloaded like this? But then you did you run it? Okay. Sure, sure. Hello. Who is this? Oh, okay, yeah. Can you call me back in the evening, today evening? Right now I'm a bit busy. Right? Okay. It will be in the evening time itself. Yeah, yeah. Call me today evening. Just confirm what time exactly. Sure. Um, so did everyone reach till this stage? एक बार ट्विटर पे कमेंट मारना। हाँ, नहीं कमेंट करो। वो चाहिए ना? हाँ वही तो फाइल चाहिए ना। हाँ कर लेना। लेकिन सेशन उनका है तो हम्म। कोई पाइटॉर्च में कन्वर्ट करना था। यार वो sorry, sir. Yeah, test part. Which one? Yeah. So anyone who has any issue with the test can view it over here. So I see there are a lot of errors in the test. So check it out. Yeah, sure, you'll get it. We'll be putting it in the GitHub repository. Yeah, we'll be running into the class. Don't miss that. So, yeah. Upload करके डाल दो.
They have different Python.
अपने में अपलोड किया है. बाद में उसमें merge कर देंगे. तो access नहीं होता. बस copy paste करना है, कुछ नहीं करना है. सिर्फ वहाँ से copy paste करवा देना. हटा बस file paste कर दिया. फाइल का सिर्फ क्रिएट नहीं होगा. नहीं होगा. रोड फाइल फोल्डर नहीं होगा, है ना? क्यों, क्या करना? वही फोल्डर्स भी है. किधर है फोल्डर? तो सब एक साथ अपलोड करो ना. वो अपलोड नहीं होता ना फोल्डर. कौन बोला? रोड फोल्डर. कुछ फाइल डाल तो अपलोड करो उसमें. तुम करने क्या चाह रहे हो? फोल्डर अपलोड करो. ये 3 फोल्डर हमारा ओपन डिलीट करके डायरेक्ट कुछ मान लो. मैं इसमें क्या कर रहा हूँ? तो पहले मोबाइल पॉकेट में रखना और फेंक दूंगा. गिट हिट किया. अब लिख गिट कमिट गिट ऐड एवरीथिंग डॉट मार्क गिट कमिट लिख. गिट कमिट माइनस एम माइनस और बाद में कुछ मैसेज डाल दें. हाँ, कुछ भी लिख रहा है. अरे यार छोड़ो. हो रहा है. चलो हो गया. गिट पुश रिमोट ऐड किया है. गिट पुश मास्टर ओरिजिन.
So everyone's model that is getting some accuracy above 95. Change the model date and get it downloading.
So
ये ऐसे ही ऐड करते हैं ये लेकिन ऐसे नहीं करते हाँ चलो हाँ कभी ये कहाँ
डॉट गेट क्या
इसके नहीं करता चल हो गया ऑलरेडी चल पासवर्ड डालना करना ये सब बात है
पासवर्ड भूल गया
sure
load modeling okay you mean to say data set loading okay Google Drive हाँ from Google Colab import file
नहीं हो रहा क्या अबे तू छोड़ तू जहाँ अपलोड किया वहीं पर कर एसएसएच में नहीं रखते हो बे पुल कर भाई पहले फिर पुश कर इसीलिए बोलता हूँ लिनक्स यूज किया कर सीख लिया कर सब कहाँ पे अनरिलेटेड हिस्ट्री कहाँ पे क्या क्या कहाँ पुश कर रहे हैं बता दो मेरे को। कर रहा है ये अपने आप पुश कर रहा है। ये पहले की तरफ है क्यों रखा है हटाना अनरिलेटेड नया डायरेक्ट को बना भाई जिप कर दे या फिर एक काम कर लो वो सारे फाइल जिप कर keep कर दे वो भी कर सकते क्या कर रहा है क्या कर रहा है बोलो कुछ नहीं जिप कर ठीक है डाल दे उसका छूट झमेला मत करना बहुत झमेला जाता है उसको तो मारेंगे तो चल लगा खत्म कर देंगे अगर मारेंगे दिमाग खराब कर दिया अरे छोड़ो गांड भरा है करेगा उसके फोन में गाली वाली दे दी है भाई सिर्फ करो हाँ क्या होगा हाँ हाँ बाजू बाजू बाहर से भागो क्या कर रहा है तुम बंद व्हाट्सएप पे डालो व्हाट्सएप में आपके ऐड कर रहा है
So actually, I'm sharing the zip file for the class in Riot. Okay, you can download it from the zip file. Open in your laptop, Riot.
So right now I've shared the this Jupyter notebook, the training that we have done, and I've shared the file. So if some of the codes are not working, you can directly upload this and run this. Okay?
पेज डिटेल्स वाला फाइल है उसमें पर क्या
अभी
हाँ
लिंक डालना
जब पेज डिटेल्स वाला एक बार पेज खुला
ये लैपटॉप
राइट काम राइट में लगा मैं मुझे डिटेल्स वाले फाइल कहाँ जैसे शेयरेबल लिंक निकाले थे ना तो छोटा करो शेयरेबल लिंक ना छोड़ो तो फाइल सपोज शेयरेबल लिंक निकल गया तो लिंक शेयर इसको इधर से कैसे सबको दो इतना बड़ा कौन लिखेगा पहले राइट नहीं खुला व्हाट्सएप है मेरा व्हाट्सएप कर सकता है ये
राइट तो इसमें भी है।
अब इसमें से डाल है काम करेगा क्या डरना था इंटेरिटी मतलब हाँ अपने काम के लिए
मैंने डाल दिया
और मैं डाल रहा हूँ
हो गया
वो मैं कर दिया
Yeah, just download this file. Download the zip file, unzip it, and then we'll tell you what to do next.
इसमें दिखा दे इसमें है Python एनाकोंडा से यूज करते हो ना डिप्लॉय करके दिखा रहा हूँ ये हो गया नहीं जुपिटर नहीं कमांड प्रॉम्प्ट कौन सा है एनाकोंडा का कोई क्या नाम है Pytorch ये भी है हाँ मिल सकते हैं मीटअप नहीं है सर मीटर मारो उसके बाद नेक्स्ट टाइम हो गया
ये आगे आगे मिस्टेक पॉइंट हो तो हम कोडिंग करो ये एमडीसीएन पॉइंटर अच्छा रहने दो बता देना
so delete the old so delete this file which is already there and use the new one which you downloaded. So I've downloaded here, so I'm just copying and pasting it there. And open up the app.py file. You can open it with any editor you want, Okay, after opening it up, you can, you can just copy paste these two things. So we trained our own model. So just change the init and the forward, functions. So just change the entire class. That would be easy. So go to. So I'm just copying this architecture and pasting it over there. And just give a tab for this class. Hope everyone are clear over here till this point. Yeah, and just change the name of the checkpoint here. So whatever name which was given over there, just replace it with the same name. If everyone are done till here, so just make sure you have all these libraries installed. Flask, NumPy, and rest all whatever is required. Yeah, if you have Anaconda installed, it will be there. So just go to file. Yeah, so just run in, follow the command as Python and then the name of the file. Okay, so I'm getting some errors. I'll just do that. So there's some indentation error which I'm getting here. You guys also have to do this. Make sure your class is replaced properly. So now it will be fine. Not sure. So just run this again. Okay, so it says no module found, so just install it. So whichever module you don't find it, just install it like this. We'll start installing it on the go. Even in Conda, you can do a pip3 as well. So you can try that. Okay, so it has installed. Uh, yeah, so Flask is installed now. So just
तो वैसे मुझे पता है क्या है।
So to install a package, you can even try this one, Python -m pip install. So I don't have image IO, so I'm just doing that as well. Okay, so this is solved now. You can install in more maybe. Okay, mostly all my dependencies are resolved. So just copy paste this URL into your browser and then and see something loaded up. So just don't click on train model, just go to load model. Okay, change in here as
Like everyone is on the same page. Like we have opened the file, replaced the architecture with what you wrote in that collab file. Till here, everyone is on board. Okay. So actually over there we use NN, and over here we are getting an instance of net model equation net. So you replace it with NN.
NN, right? So after doing that, just save it and then check it out. So yeah, so here also I got the same error.net. So just refreshing it, so it says loading is done, right? Hmm. Okay. Pre-processing.
कहाँ जा रहा है जीरो बना हुआ है पीएनजी ना क्या है
तो ग्लोबल कुछ सेट किया था क्या?
ग्लोबल तो सेट ही किया
to change this. Okay. If you guys are getting an indentation error, you have to solve it out using tabs. Yeah. Yeah. So so everyone has made this change, right? It's NN. Yeah. So just make sure you are reached till this stage, and then wait for another 5 minutes on this, and also change this as well. The name of the checkpoint file. Have you changed that? You have to store it in the same directory and rename that the new checkpoint. You have to delete the old one and just change the checkpoint file.
then I have to go to that app,
The
right?
directory. Go to
Yeah,
that.
yeah, okay. And I have changed it. So now
Yeah, yeah.
but
Fine.
it's just
Just
that
go through.
this tab is
Yeah, yeah. So run it, you'll get to know.
okay.
Just run it. Go to that app. Right. Run it out. Yeah. Okay. So there's data load. Inside that, there's one class, and then you define the class, and then put a checkpoint on that. Huh? No, no other. Image IO. Yeah, class. What's the error? Yeah, yeah. Checking that. Python space app.py. Huh? Yeah, we have to store the PT file in that directory. That's done. No, don't do the train model. Go to the load model part. So I'll show it to you. Click on this URL. Go to load model. This after running the app.py, just go to this command and then do this. And after doing this, just click on index. Go to index and then you'll get this screen. Has everyone got that? On the Anaconda side, you have to just run this command app.py. Let me know if you are getting some indentation error or something. Then it should be then the indentation should be an error. Yeah. Just make changes over here. Don't do any other changes. Yeah. Sure. I just shared all that. Ready? One. I was getting. Yeah, I'm fixing that part actually. एक से मैंने कुछ चेंज किया है और रन करना है कि नहीं करना है नहीं यार कुछ हो गया इसको रन तो कर रहा है इसको कहाँ पे डालूं So if anyone wants the app.py file, if they're getting some errors, you can use this. Yeah, so you can just copy this and take it forward. What? It's running, but then the predictions are a little skewed. Before running, just make sure you do this load model. So once the loading is done, you can go to index and then one second. Which one? Okay. राइट फिल किया हुआ है ना ये नहीं ठीक है भाई इट इज अपडेटेड all that.
Yeah, so we have uploaded that file.
You can download it and get it. Just click on this, you'll get it downloaded. Yeah. Yeah, so you have to go here. Yeah, just after this, just go to index and then give a predict. The- Which one? Oh. So if you are making any changes to app.py, just make sure you run the load model first and then you do the uh, yeah. Yeah, so first you have to go to load model and then you have to go to index. Yeah, to do that. What? App.py. Python space app.py. I,
So everybody has access to this one, phase one details. We have access to this. So basically, this you will get here. If you go to entirety.ai, uh, in the first event that we had, there we have shared it. We'll keep sharing it in the new sessions as well. So yeah, this will take you to this doc file. And in session 3, sorry, in session 2, just we have shared this feedback. So I'm putting this in session 3. We'll find, just open this feedback form and fill it. Something like this will appear, and kindly fill this feedback form. Okay. We'll share this link again on the right as well, so that is easier. Just share this, copy this and put it on the right. kindly do it, please. It will help us too.
We have pasted the feedback form here, so you guys can access it and
On the right itself.
on this thing.
Share the WhatsApp.